This video clip develops a solution to exercise sheet 3, question 4. In this question we're given a vector moving average process of order 1 and asked to verify that the autocovariance matrix at lag 1 is equal to the transpose of the autocovariance matrix at lag minus 1. As background to this question, let's remind ourselves of the properties of autocovariances of a univariate process. We have a process yt that's stationary, then the autocovariance at lag m, which is just the covariance of yt and yt minus m, that's equal to a quantity that we denote by gamma m, and because it's covariance stationary, this gamma m is crucially independent of time. If we now consider then the autocovariance at lag minus m, in other words the covariance of yt and yt plus m, then using the same notation it would be equal to a quantity gamma minus m, but in fact gamma minus m must of force be equal to gamma m as well. Okay, to understand why, let's explore the expression for gamma minus m. Because the process is univariate, I can reverse the order in which the variables appear in the covariance function. And once I've done that, I can re-index the observations, putting s equal to t plus m, and then t thus becomes s minus m, and I can recognize that the last expression is just by a definition of gamma m, because it's the covariance of two observations that are just m periods apart. Okay, now when I move to a vector process, the relationship between these two autocovariances is not so simple. Okay. The key being that I can't reorder the variables in the covariance function when it's a vector and still have the same quantity. In fact, the relationship between the two is that the covariance at lag m be a quantity gamma n, again just like a univariate case, independent of t because it's stationary, but this, rather than being equal to gamma minus m, is equal to the transpose of gamma minus m. So we're going to illustrate that property in the context of this particular vector moving average process. Let's first consider the information we're given about the error process ET that drives the moving average. Okay? We're told that it's IID with a mean of 0 and a variance of sigma. So IID stands here for independent and identically distributed, and this tells us then not only the mean and the variance, but also that the autocovariances of ET must also all be equal to 0, okay, because of the independence. Notice therefore that if ET is IID with a mean of 0 and a variance of sigma, it satisfies the conditions for being a white noise process, although we should note the reverse does not hold. Okay, so to calculate the autocovariance matrices, we need to know the mean of VT, and this we can calculate by substituting for VT and using the basic representation for the data generation process, and then using the fact that the expectation of our sum is the sum of the expectations. So we find that the mean of V is 0. Now turning to the first order autocovariance matrix, gamma 1. This will just be the expected value of Vt minus 1 prime. And then substituting in for Vt and Vt minus 1, we get the following expression that's there. So before calculating the expectation, let's first multiply out the two terms that are within the parentheses, remembering that the transpose of the sum is the sum of the transposes, and the transpose of the product is the product of the transposes in the reverse order. We then multiply out the two terms that are within those parentheses to get the following 4 expressions. Okay, so then we need the expectation of the sum of those four terms, and that again will be the sum of the expectations. Okay, so bringing the expectation operator through onto the random parts of each term. So the expectation of the first term is 0 because the subscripts don't coincide and E is white noise. Similarly with the second term. In the third term though, the expectation is going to be sigma, the variance of E, because the subscripts are the same, both t minus 1. Last term also 0 for the same reason as the first two. Okay, so we're ending up with an answer being that gamma 1 is equal to theta 1 times sigma. Now turning to the autocovariance matrix at lag minus 1, which is the expectation of vt plus 1 prime. Again, substituting in for the two v terms from the data generation process, and then going through the same steps as we did in the previous calculation. First multiplying out the terms in parentheses, we get four terms. And then what we want is the expectation of the sum of those terms, and that'll be the sum of the expectations. Okay, and going through again, the first one is 0. The second one now has the expected value of et prime, which is sigma, and the other two are both going to be equal to 0. And so we see the expression is sigma times theta 1 prime. And so we notice that gamma 1, which was theta 1 times sigma, is just equal to the transpose of sigma times theta 1 prime, which was gamma minus 1, using the fact there, of course, that the variance covariance matrix sigma is symmetric by construction and so equal to its transpose.